Distribution Unit 5, Chapter 18. We have 3 more units left. All right, the first thing I'm going to talk to you about is your chapter outline. This time I'm not going to give you a paper copy. Instead, I'm going to give you this here, an electronic copy that's on Canvas. And I would like you to go ahead and complete this on just your own paper. Of course, if you have a tablet or something, you can do that as well. So this will be due tomorrow so that you can then do your reading quiz. Most of this here I will be discussing in this video today. All right, you have now a sampling distribution class notes. Now I have it highlighted here. I'm going to talk about why I have it highlighted here in just a moment, but I want to talk about each of these definitions here. So, parameter. A parameter is something from the population, and it's described any numerical value. Any numerical value, your mean, your standard deviation, but it's all referring to the population. Most of the time, it's theoretical. The reason it's theoretical is because usually I do not know the value of the population, and because I don't know the value of the population, I draw a sample and I ask a sample. Populations are too large to know what their opinion is or what the results are of the entire population, so I have to draw a sample that is smaller that is drawn from the population. Okay? And any conclusion that has a numerical summary is called a parameter. A statistic is a sample that is described. It's a numerical summary from my sample. Statistics are drawn from my sample, and it can be mean, it can be median, it can be anything. So, this is mean, median, standard deviation, etc. And same here. It's just the difference is the parameter is typically usually theoretical because I don't usually know the population. And the statistic I do know because it's the actual people or things or whatever that I've drawn conclusion that I've measured data on. All right, so population is who or what I am studying, and the parameters come from the population. And the sample is who or what I'm actually drawing my data from. The sample comes from the population. It says it's contained. That's what that word says, contained in the population. Population mean is the average of whatever I'm studying from the population. And notice I wrote usually theoretical. And the symbol is mu. This is, it's called mu. And this is sigma, which is the standard deviation. Mu is, looks kind of like a cursive M, kind of a squished cursive M. Some people think it looks like a U, but it's actually supposed to kind of be an M. And then sigma kind of looks like an O with a circle, cursive O, and it's of course the average distance from the mean, but again, it's usually theoretical and it has to do with the population. The sample mean is just the mean drawn from my sample. And of course, the standard deviation drawn from my sample. The mean symbol is X bar, and the standard deviation symbol is S. Notice here, anything that is a statistic, there you go, has to do with my sample. Sample is statistic. And population is my parameter. So population are parameters. So that's how it would go. Population proportion, use P for the symbol for population proportion, right here. And you use P hat for a sample proportion. So let me just explain sample mean, sample proportion, simple like this. Someone's running for office, okay? So this is going to be proportion. Someone's running for president, okay? And they say, I don't know how much voter support I have. I think I have maybe 30% voter support right now. So since I don't know, I'm going to draw a sample, a randomly selected sample of maybe 100 people from that sample and see how many are going to vote for me. So my P is 0.3 because that's what my population is, what I think it is. But let's say I find that 42 people are going to vote for me. So I found that my P hat is 0.42. So remember, P hat, That's what comes directly from my sample, and P is what comes from my population. This would be the similar with means, except it would be mu. Like if I said how many people are going to vote for me, and I say, oh, okay, I think about 500 out of a in this group, and your X bar would be, let's say, actually what comes out to be is 520 or something like that, and my mean is mu is again population, and X bar is from my sample. All right, but since we don't know our population proportion, you can write P hat from the sample estimates my proportion P from the population proportion, because we really don't know this number here. We're just guessing. So that's why I'm using something to estimate it. Same thing with means, as we use X bar to estimate mu. All right, if I had chosen a different 100 seniors in the beginning, I don't know if I introduced this, but this is 100 seniors in Howard County, and these are all their GPAs, and the mean here, I already calculated for you, is 2.547 And I have highlighted here all of the seniors that have a 2.0 or above. So if I said, okay, this here, I randomly selected 100 seniors in Howard County. So there's lots more seniors in Howard County. These are just this randomly selected. And so now any data that I do from them is going to be considered a statistic. So the question down here asks you, in the example on the previous page, calculate the proportion of seniors in the sample of 100 seniors with a GPA of 2.0 or higher. And I told you that I don't know if I told you, but I counted them. There's 79 out of 100, which would be 0.79. And you can count them up here if you would like. But I highlighted all of the seniors that have a 2.0 or higher. That is a population proportion from my sample. So the hat, P wears a hat. Yeah, this is another great one, because it's a stat. So a statistic, the P, because you have P, that's population, and then P hat, that is actually from my stat. So if I put a hat on that, that means it's coming from my stats. All right, so what about these? What if I picked 10 other samples of 100 seniors? So I went to there and I grabbed another 100 seniors, and I said, and another 100 seniors, and I picked and I said, okay, how many have a GPA of 2.0 or higher? And I picked those. If you notice, I'm getting all kinds of different things. And so I have this here, I'm getting between 0.68 all the way to 0.83. But it's a lot less variability than if I look here and I try to see, oh, okay, what's the proportion of seniors I have is 0.79. Low sampling variability is what it's talking about here versus high sampling variability. Low sampling variability is when your values are closer, right? And the way you get low sampling variability is you have a higher size sample. High sampling variability, obviously the values are further. And the way you get a high sampling variability, you don't want a high sampling variability, but you have a small sample. Let's think about this. If I have n equals 10, where I'm going to flip the coin 10 times. I'm going to ask each one of you to flip the coin 10 times, okay? Flip a coin 10 times. And I want you to give me the proportion of times that you get heads. I think it'd be reasonable to say some people are going to get 0.7, some people are going to get 0.5, some people are going to get 0.3, 0.2. And so let's say I just had, people do this, and so I've got maybe another 0.5, another 0.5, maybe I got a 0.8. Anyway, I'm going to get a high sampling variability because you can see that 10 times is not enough to really get it close enough to see what the actual true value is going to be. But what if I do it 100 times? Now, you're not going to get something like 70% and 80%. Your values are going to range probably from, 60% to 55% to 40% maybe, but you're not going to have the huge difference in variability. So when this one, I would guess you might have a 20% variability, but with this one you saw we had like a 60% variability. There's a lot more because I have a smaller sample. The larger sample allows me to get closer and closer to my actual probability. All right, so for this sampling variability, it's kind of a mid sampling variability. It's not, it's not super high, it's not super low, but if we wanted it to change or we wanted a better sampling variability, of course, we would increase the sample size. Instead of us having 100 singers that we could see how many percent had above a 2.0, I could do 1,000 or something like that. But this is a pretty good variability. Okay, let's talk about samples here. If there are so many more samples, I could have had a mean of 0.754 and a standard deviation of 0.049. That's what we calculated for you. So we're saying, all right, an unbiased estimator is when my P, that's for my population, equals the P hat from my sample. So all of seniors in Howard County, all right, all the seniors in Howard County is my population. And the proportion, the P hat is going to be drawn, or is going to be the 100 seniors. And the P that I drew was what's the proportion that has above a 2.0. And the P hat, of course, was also above a 2.0, but it was from the 100 seniors. Now, if P equals P hat, we say that's an unbiased estimator. So, a statistic can be an unbiased estimator and still have high variability. So to avoid this, we want to increase the size of the sample because larger samples give smaller spread, like we just talked about. Smaller spread kind of just means the results, like the 0.7, 0.8 when I flip the coin 10 times, 0.2, 0.3, etc. And then you flip the coin 100 times and you get you get values closer to 0.6, 0.55, 0.54, 0.4, 0.59, etc. But your values are a lot closer, smaller spread. Okay, so sample proportions. Cuss and BS is back. So if I ask you to do the samples proportion, because this is going to be, we use Cuss and BS with categorical data. Categorical data is when I can put things in categories, and I describe categorical data with proportions. You think about it. If I put how many red M&Ms do I have, what proportion of red M&Ms do I have in an M&M box and bag, and so forth. So the center is just for my P is just going to be for mu. Now, this means mean of P hat, see that, is equal to P. That does not multiply. That's a period. That means that stops there. So it's just saying mu is equal to P. When it says mu of P hat, that means the mean, that means my proportion, the mean of the sample is equal to P. Unusual features are gaps, outliers, and clusters. The shape is going to be normal, but this should not come to surprise for you. It cannot be normal unless I have a sufficiently large sample. You guys learned in the last unit, how do I have a sufficiently large sample? NP and NQ both have to be greater than 10. Okay? So my spread is my standard deviation, and it is also going to be, and I have my spread here. I'll show you on right here. Where we have my normal and my mean and my standard deviation. You have the mean and you have the standard deviation is how you're gonna describe it. So you're gonna describe your shape and describe your spread. And your center, the center here is described with the mean. And remember, the mean is equal to the P. And standard deviation is PQ over S squared of PQ over N. By the way, if you flip the formula chart on the very back, you're going to see where it has these formulas. So go ahead and get your formula chart out and take a look. find where it says sampling distribution. It's on the back page. Finally, we're on the back page, and you'll see square root of PQ over N, and you'll see the mean is equal to P for standard deviation and for mean. For sampling distributions, you're going to be looking for sample proportions. Okay, so however, you have to have, the population has to be sufficiently large. And so what does that mean? We learned the 10% rule. This is the 10% rule, is that you have to, in order for me to be able to draw this, we have to make sure that my sample is not drawn more than 10%, because we don't, as we learned in a previous unit, in order for us to have independence, we have to have a 10% rule, and that is the only way that we're going to be able to have the standard deviation of square root of PQ over N. All right, proportions are used. What did I just tell you? Categorical data. So, categorical data versus quantitative questions. Categorical data is proportions. Quantitative data, we use means. So, means, as I said, right here. So here's an example. Use the data from the first page. Suppose I randomly selected 100 seniors of Maryland and recorded each one's GPA. I'm interested in knowing the average GPA of each senior. So the same thing, the same idea in Howard County, we did this and we found the mean of the GPA of 100 seniors. And these are the 10 means I found. Okay, so what does the sampling mean look like? So this same thing, I could have done the same idea. Just like this last one, all I did is I said, hey, what's the proportion? So the question asked, what's the proportion of people that have above a 2.0? Where now sampling means is saying, what is the mean? That's the difference. Proportion is categorical, quantitative is means. So for the means, it's the same thing. We're going to cuss and BS again. The center this time is your mean is equal to mu. And the mean of x bar, so you see that? The mean of x bar is equal to mu. The shape, again, is normal. But I have the same assumption, sufficiently large. Did you see we had the sufficiently large assumption here? Sufficiently large. This is proportion, so I have a P and a Q. I don't have a P and a Q, so let's go backwards to, remember when we did experiments and observational studies, I made your N be greater than 40. We accept in AP Stat 30 or 40. I like to use 40 when you're doing your experiments and observational studies because you get better results. You get a little bigger sample, better results. But I will tell you, the rule, the minimum is 30 when we're actually in our books and doing some of the things that we're doing. You can use 30 in order for me to say the sample is sufficiently large for normality. So with means, I use 40. With proportions, I use NP and Q greater than 10. My spread is also still the standard deviation, but it has a different formula. And now it is sigma over the square root of n. Sigma, remember, is my population standard deviation. So remember we had we had S for standard deviation and sigma. And this is now when I'm using sigma. When we put our one variable statistics. The central limit theorem says basically if n is big enough, then I'm allowed to use a normal model. And with a mean of mu and a standard deviation of sigma over square root of n. So n is large enough, which large enough, again, you can use bigger than 30 or you can use bigger than 40 like we did in the fall. So here is what I've just taught you. Basically, the conditions I use, the acronym, yes, I got an acronym for that one, is RILT. And this is my acronym. This is not anyone's special acronym. It's my acronym. So if you put RILT on your paper, RILT means nothing. But here's the deal. For proportions, I want to be able to use my mean of P hat. I want to use the mean of the population. And I want to be able to use the standard deviation as square root of PQ over N. And for means, I want to be able to use the mean of the population as the mean of my sample. And for the standard deviation, I want to be able to use sigma over square root of N. Or this, sorry, So in order for me to do that, I have to have this RILT conditions met. So let's look at RILT. R, simple, this is identical. It means randomly sampled. So it's a good representation of the population. So let me talk about that. Remember, we've talked about that before. I don't have to have a random sample. I have to have a good representation of the population. However, if I take a random sample from the population, typically I get a good representation of the population. So it's the easiest way to get a good representation of the population. So if your problem says it's randomly sampled, you've got this condition set. Or if it says it's a good representation of the population, or there's other things in there that make you believe that, then you are set with that condition. Both of them has to have independence. Each sample has to be independent from each other. I cannot have a connection if I'm interviewing men and there's their favorite color, and if all of the men I'm interviewing are in a club called Favorite Color of Yellow Club, then obviously that doesn't make sense. There's a connection between all of them where they all like yellow, and then there wouldn't be independent. So I need to make sure that they're independent so I can get a good representation of the population. All right, this is where it differs. If it's a proportion, I have a proportion. I have a P and I have a Q. And so I have to check NP and NQ greater than 10. If it's not a proportion, then I use sigma over square root of n. So if it's a proportion again, I use 10n is less than n. If it's a mean, I still use 10n is less than n. So I can use the 10% rule as the same. The only difference in here is my NP and Q and my sigma over square root of n. And that's it. And that's all you have to do. All right, so I'd like you to go ahead and go back. Your assignment is going to be this electronic copy that is on Canvas, and it's posted on today's calendar, and go ahead and read the chapter and do this, and have it uploaded by tonight. Okay, thank you very much.